And please use the Q&A tab at the bottom of your screens, because whilst it's not possible for you to actually ask questions of the presenter direct, if you log your question in the Q&A tab, I'll work through them live. And if there are too many, we'll select some representative ones to ask. Now, we'll ask our questions of the presenter at the end. Of course, if you have a burning desire to follow up directly with our presenter after the seminar, please do so. And as in the case of our current presenter, it wouldn't take much time on Google to find out how to contact the person. Now, today's presentation is very timely and topical. What a bounce back our agriculture industry is experiencing after drought and fires. The Bureau of Meteorology's latest 3-month climate outlook, that's September to November this year, issued just a couple of weeks ago, indicates the spring rainfall is likely to be well above average in most cropping regions. And that's going to lay good foundations for our upcoming summer cropping season, as well as finish off those crops in the current winter season. In fact, our winter crop production in Australia is forecast to increase by a whopping 64% this season, which is actually 20% above our 10-year average up until year 2019. The area planted to summer crops ahead is forecast to rise by nearly 200% on last year. And of course, last year we were being ravaged by drought. So to our speaker, the topic of today's research presentation is around Graincast, which is a tool focused at monitoring Australia's cropping landscape. I'm delighted to introduce our presenter, Dr. Roger Laws. Roger Laws is a group leader and farming systems scientist with CSIRO Agriculture and Food. Having completed an applied science honours degree at Adelaide University and a Master of Ag Science at the University of Melbourne and a PhD at University of Queensland. And I would expect, Roger, that some of your co-peers from your PhD days may be watching. Roger's PhD was evaluating sugarcane block data with spatial mixed effect models. Roger joined the CSIRO in 2002 as a postdoc in Townsville to work on ecological modelling of weeds, and Roger moved to Perth with CSIRO in 2007, where he focused on many aspects of farming systems research in crops and livestock, leading numerous state and national projects. Roger's co-authored 60 journal publications in areas ranging from crop modelling, crop nutrition, crop rotation, applied statistics, ag economics, farming systems, crop nutrition, precision ag, weed science, pathology and remote sensing. What a wonderful toolkit Roger brings to this particular challenge. Roger has recently led the Graincast initiative in CSIRO, what he's going to talk about today. The objective being to develop and deliver the science necessary to build and operationalise a national crop monitoring platform, providing data services to many facets of Australian agriculture. So it's with great pleasure I introduce Dr. Roger Laws to the virtual podium to tell us more about the Graincast initiative. And bear in mind, please log any questions you have under the Q&A tab at the bottom of your screen. Welcome, Roger.
Thank you, David, and thank you very much for the opportunity to present in this consortia. I'm delighted. So without further ado, I'll share my screen. So thank you. So this project is all about how we went about in CSIRO monitoring the Australian cropping landscape. And the project has been named after the fact, Graincast. It wasn't initially called that at all, but it's about the process that we went through to come up with this capability at a national scale. When we embarked on this, and it was first posited around 2016, 2017, that we should think about how do we go about monitoring the landscape. The question was really quite simple in one line. It was, we need to get estimates of crop tonnage in near real time to deliver to agribusiness. Those products, they had to be scalable in both space and time. They had to deliver insights at the Subpaddock scale for people interested in precision agriculture, the Paddock scale for people that might want to integrate this information into products that farmers and consultants might use, like, for example, back paddock and farm record keeping. We needed the information to be delivered at the farm scale, if that was required, where people might want to understand how to market their crop within a farm. Obviously, that then extends to thinking that process through at the regional and state level, where questions around logistics and finance might be considered. And then finally, there's a need for some national statistics to feed into government planning and policy. We recognise that each of these possible use cases created a bit of a dilemma. There wasn't a system out there that could cover all of these different requirements. So what that meant was we sat down and we thought, well, we need to develop information flows that we can access and then disseminate, and do this via modern digital platforms. The first real challenge was breaking this big problem of tonnage down into its respective components, and recognise that we needed to tackle and use different types of science for different problems. So on the one hand, we had to identify crop type or crop ID. It was considered vital because to get planted area and tonnage, you needed to know what crop was planted where. There are relatively simple heuristics you could use, like what was planted the previous year, but as you would all be familiar with, coming out of a drought, often in extreme situations, those generalities don't hold and need to be adjusted. Then we also needed to estimate crop yield. Now, at one level, we had the APSIM crop model. It's widely known. It's been developed over a 30-year time horizon. But unfortunately, that requires a huge number of parameters to run. And whilst it can give you very valuable insights, it was problematic when you want to run it on 60 million hectares and deploy it at the landscape scale en masse. So we really had to challenge, how do you model crop yield, and are there tools that we should be considering to rethink that strategy? And then finally, this question around data aggregation was troubling. It's one thing to come up with state boundaries. They're not too difficult to access, but once you want to operate at the farm and paddock level, it become onerous to draw paddock boundaries around individual fields. So we then had to create an integrator of data to allow us to package information up to a level that an organisation could make use of it if they so desired. So we then also focused on building a product around paddock boundaries. This multifaceted problem means that we had to assemble a fairly large and complex team. We had user experience and software engineers, we had crop modelers, we had remote sensing scientists and data analysts, we had GIS technicians and people whose specific job was to organise the training data. And then finally, we had a series of postdocs involved whose job it was to take some agency with these problems and see what the next generation of scientists could uncover and develop when put in an environment where they can explore and create. But this amazing team basically means that all I am is the face of that team, and really this is an output generated by a large number of people who were working together from all states in Australia, from 3 different business units in CSIRO, from agricultural and food, land and water, and Data 61, where we came together to address this problem. The big challenge initially was that everybody was talking about machine learning and using various types of machine learning to address the problem. But as many of you would be familiar in the digital age, the first problem with machine learning is that you need a suitable supply of training data with which to build the models. That became our absolute priority from day one. This required a coordinated plan about how we acquire such data, firstly to develop the science, which is one thing, but secondly, that acquisition of training data needed to be operationalized at a national level so that we could continue to deliver these products at scale. Also, at times we recognized that to produce products around new crop models, we needed yields at Subpaddock Scale, and then we also needed Paddock Boundaries. So there was a whole process involved in creating those libraries. Similarly, we needed national land use marks, state boundaries, shire boundaries, and other cadastral data that can be accessed. Again, all to deliver information to clients as they required it. The fourth challenge was very much around building a national workflow for training data acquisition, processing, and storage. But there is so much more to data science than accessing data and crunching it. You need to set up a legal license to operate. We put up multi-agency data transfer agreements across a whole host of organisations. We have to focus on the social license to operate and the human ethics. So all this work was conducted with ethics approvals and where we were constantly monitoring our social license to operate and what that meant, and then challenging ourselves on those processes. There was components of ancillary data processing around climate and soil grids. And often we worked with industry to drive product creation. We needed to understand what the industry's needs were. And in something that we don't usually do, we actually took clients on very early in the research process simply to understand what we needed to produce to create a national product. And the research was always conducted with a goal to operationalize the outputs and commercialize the process. So in essence, those slides can be broken down into the key components around training data, crop modeling, acquisition of satellite imagery, processing of that satellite imagery, advanced analytics with machine learning and AI, and then finally software engineering and design, where we engaged with people to understand how they might use the technology and what features they might like in a digital delivery system. So now, breaking down into the individual components, I'll jump into our first major achievement with regards to the science, which was the development of the C crop model, which was a satellite-driven crop model. It is basically a simple remote sensing crop productivity and yield model. It works off gross primary productivity that estimates plant and models the plant carbon mass. To do it, we needed crop type and climate. And what we do is we estimate the gross primary productivity via an estimate of FPAR, plant available radiation, and LAI, all of which is extracted from an NDVI signal. And that NDVI signal is used in time series. To give you an idea of how this works, we have a total assimilation. And then from that, we have some tuning, effectively some tuning parameters around an allocation fraction. That then goes to a leaf mass, and with an estimate of, or a temperature-based empirical conversion function, we come up with a grain mass, all tuned off industry information. This process means that we can take this generic framework and move into another region, another crop, etc., with a relatively straightforward process. To give you an idea of how the allocation dynamics change through the season, we see that early on we have a lot of that allocation fraction is going into the roots, and then as the crop develops, it moves into the leaf. That then gives us an amount of carbon that's allocated in terms of total assimilate, and we can see that it effectively grows a crop. It is a semi-process model. This then turns into a look at how gross primary productivity on the chart below translates into both a leaf mass and changes through time, but also relates to FPAR and the amount of radiation that's intercepted by the plant. So what we have is a model working off the fundamentals of photosynthesis, using the NDVI signal that you can extract from a satellite as part of that, informing that photosynthetic process, building a carbon pool, and then using that to estimate a grain tonnage or grain yield. So how good is it? So our first generation, our first attempt at Subpaddock Scale, we were coming up with R-squareds of 0.66 and a residual mean squared error of 0.72 tonnes per hectare of 1,264 data points at this point in time. We are looking to refine it. We have since developed the model somewhat further. So the HF model is the standard GPP-driven model that's in the literature from 2003, produced out of the US. The C-crop model there is showing with some more data that was used after the original training set in the published paper. We came up with R-squareds of 0.75 and an RMSE of 0.7. And a new model, the crop SI, starts taking into account precipitation and mid-season and late season maximum temperature. So what we realized with C-crop is, as a functional model, what it was doing, it was focusing on building that carbon mass, but we weren't worrying too much about the end of season processes. We've now included that and assembled the components with a support vector machine with crop SI. So we're now starting to explore how best to assemble the dynamical attributes in a crop model. Give you an example of how one of the advantages of working with C-crop is this is our current image extracted from MODIS and then processed, is that we're able to produce, once we extract the MODIS imagery with the climate grids, we are able to extract a national output for wheat or canola or barley in 17 minutes off our high performance computing facilities. And then once we have that map, we update it every 2 weeks across the season. And our only blocker really is the speed with which we can access the processed MODIS imagery from the USGS website. Give you an example, we can scale it down to the state level. This is our 2018 estimates for Western Australia conducted on the 30th of September. But then you can start using this information at the field or farm level. So here is the progressive nature and the way we can even visualize and use that data at the field level. So for a farm, they can see how the crop actually grows and progresses through the season. And what this does is it means a land manager can start looking at this imagery early in the season and determine which crops are likely to yield more, which paddocks might need some sort of attention or some other management philosophy. And the idea is to provide this information fast enough that instead of just working with a generic variable like NDVI, you actually have a tonnage that you can work with. So you can now work out the relative difference between paddocks in terms of actual grain yield. Moving on from C-crop, we then moved into crop identification and land use mapping. And our first problem here was acquisition of training data. Most of the machine learning algorithms, not most, all of the machine learning algorithms that you can deploy into remote sensing at the moment need local acquisition of training data. Creating a classification, whilst you can technically do it in one location and deploy it into another, and we certainly experimented with that, we generally found that the classification accuracies, when you do that, declined considerably. Obviously, we're using as many satellite platforms as possible. So in the earlier days, we were using Landsat 8 and Sentinel-1, where we were processing that data in CSIRO. as we've evolved, we've moved to a Sentinel-2 platform as well. Obviously, we need really good land use marks to assist with the classifier, make sure we're only working on the cropping land and we're not trying to include things like roads and native vegetation as well. And then we're using various forms of ML classifiers, predominantly random forests. We played around with support vector machines early on as well. And then later we started exploring how we might build a deep learning approach that takes in using convolutional neural nets that can take in a lot more information than what we currently have. In 2017, when we first tried doing this at scale in Western Australia, we literally just went on field trips, acquiring data by spotting crops and trying to acquire it. I think that was our first genuine lesson in how difficult this can be to do when you need training data in every image that exists across a large landscape. And this was only one state. We were yet to do it in other states. That meant that we focused on formalizing relationships with multiple parties, multiple potential end users who were interested in acquiring that data. And through the process of delivering this information and this output and commercializing it through digital agricultural services and working with them to develop this approach and this collaborative approach with industry, digital agricultural services have now got a training data acquisition process in place that allows them to classify multiple different crop types, including tree crops and various pastures, and then run those algorithms across the continent where there are training data present in pretty much every Sentinel-1 and 2 scene across the continent where crops are grown. And that is actually the vital component in building a crop classifier. To give you a bit of an example of some of the earlier classification we did in 2018, we were able to deliver all of Western Australia. We first developed a product on the 5th of September in 2018, and as you can see, the results for that first classification were not spectacular. We ran into problems with a very late start to the season and problems with cloud, and it meant that we had very little imagery available to us. And it wasn't until November that we were able to get highly accurate classifications in the order of 80%. To give you an idea, our classification accuracies early on, the overall accuracies were only 53% with a kappa of 0.36. In other words, sort of an agreement with the data. Users and producers' accuracies were good in canola, but in the cereals we were always having problems. As the season progresses, those overall accuracies increase, and we start doing a little bit better in the cereals as well. But it's still a challenge at some point, and it's not until the November classification where we were able to increase those accuracies in Western Australia and get a kappa of 0.7. And this is one of the challenges, is what we are finding when we're engaging clients, is their method of how you engage with a model and use the data differs to how a scientist will approach it. They will literally walk into a field and say, you classified that as wheat and it was barley. I don't believe your model, even when you've got a producer's accuracy of nearly 90%. And this is the sort of challenge we have, in that going from a statistical approach to a practical, pragmatic perspective is something that we need to think through quite carefully with how we deliver and disseminate this information. As an aside, with digital agricultural services, they have been able to improve significantly on our earlier methodology by switching to Sentinel-2, and they're accessing early season Sentinel-1. They're able to do this through the Google Earth engine, and the accuracy that they are achieving across 3 classes is over before September. So, and this is because their clients are demanding early season predictions. And when we took this through a commercialisation program through CSIRO on Prime, that was something that always came back to us. It wasn't about building a classification. It was about building a usable classification and delivering that to industry fast and on time when they wanted it for their purposes. Finally, one of the next pieces of, technology that we focused on was developing the technology for Paddock Boundaries using fairly advanced machine learning and a data-driven approach with limited pre-processing. Again, it needed to be scalable. So what we were doing was taking an input image, using semantic segmentation, where you're labeling every pixel with a class, and then using instance segmentation, where you're effectively creating objects from the classified pixel, which in effect your object that you're creating is your paddock boundary. Again, accuracy is vital when reporting on model performance. I think the first thing that we do is talk about how well the model is performing so that we can engage with the industry and let them know what the under-segmentation and over-segmentation rates are and some idea of what overall accuracy is. Because whenever somebody starts using your technology, people are very quick to let you know when it doesn't work. So you need to be able to back up your model performance with an accuracy assessment. Just to give you an example of the sort of product that is produced by Paddock Boundaries, we were able to generate 1.7 million boundaries across 60 million hectares of the cropping and mixed livestock zone, mixed cropping and livestock zone in Australia, which you can then colour in with crop ID and start looking at how the land use can change and evolve across Australia and deliver that in a nice, sharp way rather than just as a simplified pixel, which is what we were doing with the earlier versions of crop ID. It allows us to create a national product, and I think probably the important message here is that what we did was the original model was built off publicly available data out of South Africa, which can be accessed. But then we also created 30,000 training paddock boundaries in Australia to then train that model effectively across multiple different landscapes. And this is an important part in improving the accuracy. And if you would like more information about the paddocks, you can access it on the CSIRO website where it's available as a data product. The Graincast app was a different take on how to work with the industry and provide information. We actually engaged with a lot of growers and asked them what they would like. And they liked concepts like Absent, but they were problematic to use. And they wanted the information now, and they wanted it while they were driving around in the paddock if they could get it. And they didn't want to have to parameterize a complex model. So we decided to create an app that gave them output from Absent, used the national soil grid, used the national climate grid, and could deliver an estimate of soil water status and then give you a crop yield prediction with climatology, assuming unlimited nitrogen. To do this, we developed the product quite quickly by both engaging with growers and then running through a Google design sprint workflow, and then testing that with UX engagement and user experience. That led to the creation of a quite simple interface that gives you a spread of yields in terms of a yield potential and a soil water status, all based off using Absent. We found that the uptake and use of the app increased quite quickly from its early release in 2018 through to 2019, whereby early in the season, we had executed over 5,000 individual runs of the model, and this has continued to grow since then. We're now well over 300 paddocks being used and monitored all the time. Across the nation, it's being used in various places for all different types of crops. And it's about trying to understand what exactly is it that people want and how can we best deliver this technology to them and the information that they actually want. So most of this work has been published at some level. So we have a reasonable amount of literature on crop yield mapping and forecasting, where we walk through the various iterations of crop models. Similarly, thinking about training data acquisition and crop identification. We've looked at packaging issues around how do we cope with rare and infrequent crops. Are roadside surveys okay? How do we cope with differences in the class proportions, etc. So it's walking through all of the statistical issues around collecting sufficient quantities of training data to conduct a crop identification and machine learning output. And then our paddock boundary work has also been published, looking at image segmentation and object detection. So without further ado, I'll hand back to David, and thank you very much.
Thank you, Roger. Roger, perhaps go on mute.
Yep.
Look, thank you, Roger. Very informative, and questions were piling in, I must say, and good solid researchy ones too. So if I may, I've got some questions pretty well in order of your presentation. So you mentioned earlier in your yield records, with the yield forecasting yield records, 6,000 yield records across 6,000 individual paddocks per year. Were there multiple records by pixel in a paddock? Or are they per paddock?
Yeah, we did both, David. So we looked at sub paddock pixels and then also aggregated that data up. So you can get two different estimates of model performance. You start running into issues around spatial autocorrelation. You have to be cognizant of that when you're calibrating your model. But yeah, absolutely.
Okay, thank you. Another question. I'm going back to your partitioning of biomass in the modelling. The question is around the separation or the delineation of productive leaf mass from for example, weeds and the influence of weeds, if at all.
Yeah, look, to be honest, you don't capture it. You're looking at, so the only way to think through what weeds would do to a crop is weeds, hopefully, are not the dominant species. If they are, you've probably got a problem. So once you've classified it as a wheat crop, and that's what you've identified it as, what the weeds might do is lower the yield of that crop and lower the total leaf area of the entire system, and limit that yield, and it will capture that to some extent. But sure, it's not taken on board. We're using Modus to do this, so that's not possible to discriminate at this point with that approach.
Okay, and there was a question which did get clarified in chat, but someone did ask about the ground resolution. So with Modus, it's 250 by 250 metres, 6 hectares. Yep. And where the sentinel imagery was used, was that was providing a sharper product around what, 10 metre pixel or something?
Yeah, so we've got a sentinel image where we're working with a 20 metre pixel. We're upscaling it just a little bit because it gives you better clarification. But generally we work with, to do the national prediction quickly, you have to go with Modus. You couldn't run all of Sentinel in 17 minutes.
Yes, of course. Now there was an eagle-eyed observer. When you were running your model comparison graph slide, there was a weird feature around the 2-ton mark. I happen to know the individual, and I know they're very sharp eyes indeed. I mean, that was a very detailed question. Have you got any comments about, I guess, the model conformance at different parts of the range?
Yeah, we actually know a lot about that little kick. We've stared at those graphs long and hard. Basically, what we're actually picking up is some regional differences. So we do know that the error structure is slightly different in Western Australia to what it is in the eastern states. It's probably generation 3 will start trying to overcome those little issues.
Awesome. Thank you. Now, a question around cloud and how you dealt with cloud, and in particular, this one's obviously got a Queensland interest. How you deal with cloud? Sure.
Cloud's painful. So basically, with Crop ID, we've been using Sentinel-1 to a large extent when we are running into problems with cloud. So the radar overcomes that. With regards to crop modelling, what we're actually using is the 16-day mosaic from Modus. So that's the other way of getting around cloud. They're the two approaches that we use, yeah.
Okay, thank you. When it comes to the yield modelling and I guess smartening up the yield forecasting algorithm, were any IoT-based sensors used? Any local measurements used to augment that?
Yeah, good question. So at this stage, with the satellite-driven model, no, because you couldn't develop a methodology that uses a local sensor and then deploy that at national scale. You would need sensors everywhere to do that. With regards to the APSIM model, so there is another piece of work not attached to Graincast, but we are looking at, okay, what if you wanted a really nice tight prediction of a field? Then how do you bring this sensor data into an APSIM crop model, properly parameterize it, et cetera, et cetera. And we've got the workflows set up for that, but that was actually outside of the Graincast brief.
Okay, thank you, Roger. Keep the questions coming, by the way, but the list is growing out under us, but we do have room for some more. A question around the app and the use of the soil grid data. The comment was around the size or the resolution of the gridded soil data and how accurate or what the impact was in relation to soil moisture and hence the model performance.
Yep, great question. So the Soil Landscape Grid of Australia currently operates at 90-metre resolution. That product is machine learned off the Australian Soil Classification Grid. Now, we know it's not perfect, but the Graincast app was built when we asked people, what about soil type? We actually did a lot of testing and they said, give me a number. And the only way you can give someone a number quickly without digging a hole is to basically grab the data off the Soil Landscape Grid and use it. And I think this is a really important concept in digital ag. And that is how good a model do you need to make the decision? It's not how good a model can you build, because very few people want to pay you enough money to go and build the perfect model with all the data you need. So this is actually highlighting a big challenge that we have in agriculture. How much investment in models and model construction and sensors do you need to, I don't know, change a nitrogen decision, which has a marginal value of maybe only a few dollars a hectare. So this is actually what we're up against, not a statistical question of how do you build the best model you possibly can.
Thank you. Roger, any movement in the tree crop area in relation to crop identification and even perhaps the yield end of the game?
Oh, look, I think tree crops are just another part of the classifier. If someone's, the way that you are able to implement the classifiers these days means that as you acquire data on a land use, you'll build it in. And if a client starts wanting that information, you just deliver it. Cool.
Canola was a standout performer in accuracies. Any insights into that? Why you think that would compared to the other cereals?
Yeah, it's yellow.
There you go, Mike. There's your answer for you. I can explain later. Very yellow. And did you find the need for to have different models for different cereals? Yeah,
good question. We're still evolving. So in the early days, as in 2017, we were classifying scene by scene. What's happened now is you're able to do a national classification and use all of the data across the continent and work with an image collection within Google Earth Engine. In the early days, we weren't using Google Earth Engine. We were using the NCI and ESA and then running it all through CSIRO's computers. And that actually slowed us down because it meant we had to download all the imagery before we could use it. Through the cloud-based service, you no longer have to do that. And that's actually been why it's possible to start generating outputs this early in the season. We used to lose weeks just downloading imagery and then finding out it was cloudy and then, paying for those downloads. And a lot of those problems have been overcome.
Yeah, very good. Thank you, Roger. Question, since you forecast early in the season, what about uncertainty in relation to climate or unpredictable or unpredictable problems like crop disease, for example?
Yeah, good questions. Basically, I'm going to be honest at this point. So the crop model, the app is using straight climatology. So what that means is you use the weather up until today, and thereafter you use just the historical weather that could have happened as a distribution. That is not the cutting edge of the integration of climate models with APSIM. We actually have used the latest climate models out of the Bureau of Met and brought them into APSIM so that you can bring that information in to get a different prediction. But they are still in the development phase and not ready to be released publicly, to be honest, at this point. As for something like disease, we're basically providing a forecast of yield potential. So it's the upper bound of what you could expect to achieve. And if something like disease came in, the APSIM model wouldn't give you a good prediction. In contrast, the C-crop model, which is working off LAI and FPAR, will actually pick up disease problems. So if you had a diseased crop, it will let you know because it will downregulate the amount of carbon mass that's being produced that can be turned into a grain prediction.
Yeah, thank you, Roger. Question about the calibration data sets. For example, with regional yield data like through CVH, Emerald Grain, GrainCorp, are those sort of data sets available to validate model forecasts at the end of the season, for example? And if so, did you have access to those, or would you consider those?
No, we never had access to those, and we were dealing with some of those clients that you listed.
Okay. Running to the end of questions, you've done well. It's almost as long as your presentation, but yeah. You mentioned two climate variables: mid-season rain and late-season temperature, I think. Why did you land on those?
Look, it was done purely with machine learning. So there was a whole suite of variables put in, and it was a classic case of let the support vector machine pick. So what it's gone and done is it's picked things like heat stress and frost as impacting on how your amount of carbon translates into yield. And that's not surprising. So when those variables fell out of the machine learning, I didn't argue with it. I didn't sit there and think it was rubbish. And the fact that there's a mid-season amount of rainfall in there also tells you that that's influencing the amount of stored soil water at a critical point in the crop's growth. So again, that made perfect sense as well. And I think this is one of the things we have to think about with machine learning. You've got this balancing act between understanding the processes and then second, looking at the model output and asking yourself as a crop modeler, does this make any sense? Because every now and again, machine learning does do interesting things that clearly tell you that it had a bad day.
Yeah. Now, you mentioned a couple of times that important relationship between the statistical accuracy of a model or a classifier versus effectively the probability that a single person will experience the correct answer and hence have confidence in it. How did you address that issue of clear communications regarding the reliability of data to the participants? And how did you actually implement that as a feature?
Sure. You need to spend a lot of time with clients explaining the process to them. I don't think there's any other way. I didn't formalize that strategy. It's really just being open and honest. I never walked into a room claiming that we could deliver 100% accuracy. It was about explaining that there is error with every model. Every model, we all know that. And then explaining to the client that they need to understand there is error and it won't be perfect, but it might be good enough to make a decision. And I think the kappa value is something that I often found useful because it is an assessment that says, what is the what is the percentage that this is better than random? Once your kappa value is above 0, you know you've got more information than knowing nothing. Yeah. So
I can hear the applause from the statisticians in the audience already. Now, someone did seize on a technical point you raised around your support vector machines.
Sure.
And so forgive me, because I don't know this, so I'm hoping you can work this one out. So how did you set the tuning parameter? How do you go about setting things like kernel, scale, penalty, those things?
Oh, you just iterate through them, to be honest. And to be fair, I would have to go back and check the paper for the specifics, but the publications are there, and it is written up. So yeah.
Understood. And just for everyone's reference, remember we have a recording of this presentation that will be made available to you. So every slide Roger flashed up, including the publications, and quite a few questions on that, you'll be able to scroll through and get a freeze frame on those. So thank you. A question just around, and the last question I might add, around the mid versus late season of crop developments. Did you employ a Paddock Scale effectively through your crop phenology, or was that some?
Yeah. Good question. Look, you can't when you do this nationally, and I'll tell you, there's a really easy reason why. When you're in somewhere like, let's say, Esperance, in southern Western Australia, you've got a long growing season, it's quite cold. If you move into the Darling Downs where it's warmer, your Paddock scales are completely different at the same point in time for the same sowing date. Moving into phenology gets really challenging at this point in time with anything else, without bringing in an awful lot of additional information.
Thank you. There is a comment, look into Bayesian optimization rather than grid search for SVM tuning, but I think that makes sense to you. Cool. Thank you for those very technical points in the audience. Ladies and gentlemen, thank you for joining our seminar. Thank you, Roger, on behalf of us all. Silent applause ripping in. I just wanted to alert you all that our next presentation will be early next month, 13th of October. 2 p.m. on Tuesday. We only pause for the Melbourne Cup at that time slot. And we'll be talking about our recently completed beef red meat blockchain project involving the teams from QUT and Beef Leisure. So really looking forward to that. One of our projects is coming to a conclusion, and there's some great experiences to share, not only around the legal and the technical and social elements of deploying blockchain in the red meat sector, and there'll be a demonstration of the smart contract and Beef Legends elements of the project. So watch out for that. We'll send the announcements out very shortly. But look, Roger, on behalf of us all, thank you for your presentation. If any of you have any further questions you'd like to ask of Roger, please feel free to contact Roger direct and have no problems finding Roger through the CSIRO website. If there's anything that we can do in Food Agility to improve your research seminar experience, I'd love to hear from you. By all means, follow us on Twitter. We've also instituted a research innovation community on LinkedIn. We will post that link to chat, to the chat window on this. We'd welcome your comments around this presentation, but others, and some of the challenges of the day that we're all facing. So we look forward to seeing you at our next presentation. Thank you again, Roger. Stay safe, stay connected, and stay sane. All the best.
Thank you.